Project objective: to solve complex problems involving multiple integrals manually and verify the results using mathematical software. Software selected: MATLAB. We chose MATLAB for 4 main reasons. First, it allows us to calculate exact fractions, which perfectly verifies our manual math. Second, its built-in functions are specifically designed to handle complex integrals. Third, writing the code step by step matches our manual logic, directly following the project's rubric. Finally, mastering MATLAB now gives us a strong foundation for our core electronic engineering and microelectronics subjects down the road.
Good day everyone. Today I am presenting a double integration problem solved by hand and verified with a MATLAB script. Our goal is to evaluate the integral of the function 4 power of 3y minus 3y squared over a rectangular region where x goes from 0 to 1, y goes from 1 to 2. So this solved by hand. We first integrate the inner part with respect to y while keeping x constant. This changes our term to 2x power of 3y squared negative minus 1 minus y power of 3. Next, we plug in the upper limit of 2 and subtract the lower limit of 1, which simplifies our expression down to 6x power of 3 minus 7. Finally, we integrate this remaining expression with respect to x from 0 to 1. This gives us 3 per 2 x power of 4 minus 7x, and substituting our boundary leaves us with a final calculation answer of minus 5.5 unit square. So to make sure our math is completely correct, we can verify it using the computer coding in the MATLAB script. We define our mathematical function using element-wise dot operator, which is standard coding practice. We then define our exact boundary for x and y and pass everything into MATLAB built-in integrate 2 function, which automatically computer and double integral. So as shown in the command window output, the script successfully calculate the exact same solution of minus 5.5, proving that our manual math and our code match perfectly.
Hello, my name is Caleb. I'm going to present this question 2 for this report. So as you can see, the left side is the MATLAB simulation and the right side is the handwriting solution. So as the question asks us to change the equation into polar coordinate, so we will using these 3 formula to change the equation into polar coordinate. The first is x equals to r cos theta, and y equal to r sin theta, and lastly we have r squared equal to x squared plus y squared. So we're using this formula to change the equation into polar coordinate and do the double integration. So for the first integration, we do it normally, but for the second integration, we need to use u substitution to do it, because in the equation have cos and sin. That's why we need to use the u substitution. And then lastly, we can get the answer is 682 over 5. And then let's see about the MATLAB part. So I put the equation inside the MATLAB, and then I ask the MATLAB to do the integration by using int function. So lastly, we also can get the same answer, which is 682 over 5. So as you can see, my answer is completely same with the MATLAB Simulink. So this is my present for question 2. We move on to question 3.
Hi everyone, my name is Zaim. Today I will walk you through my MATLAB script that calculate the surface area of the paraboloid z equals to 9 minus x squared minus y squared, where z greater or equal to 0. I divide the code into 4 clear segments so it is easier to follow and the result matches my manual calculation. So for the segment 1, I do partial derivative. In the first segment, I define the function fxy, then I calculate its partial derivative with respect to x and y. Then derivatives are important because the surface area formula involved those derivative. Next, segment 2, region of integration ROI. Next, I set up the region of integration. Since the surface circular when projected onto the XY plane, I switch to polar coordinate. The radius goes from 0 to square root 9 equal to 3, and the angle theta goes from 0 to 2 pi. This covers the full circle. Segment 3, polar conversion. In this part, I substitute x equals to arc cos theta and y arc equal arc sin theta into the integrand. Then I multiply by r, because in polar coordinate the area element is arc d theta. This gives me the correct integrand for the double integral. For the segment 4, we just evaluate the integral. Finally, I evaluate the double integral symbolically and numerically. MATLAB gave me both the exact symbolic result and the numeric value. The numeric answer matches the surface area I calculate manually, which confirms the script is correct. So, by breaking the code into 4 segments, reactive region, polar conversion, and integration, I made the process clear and systematic. This approach not only helps me understand the math, but also ensure my MATLAB output is consistent with manual calculation.
Hello, Professor. My name is Chiu Shishun from Section 2, Group 2. Today, I'm going to present my MATLAB solution for question 4 group project. So, firstly, the first line, we initialize our XYZ variables using the SYMS command. This is a very crucial step because it tells MATLAB to treat this as algebraic symbols, allowing us to get an exact fraction at the end rather than a rounded decimal. Next, we define our integration boundary exactly as we established them in our manual calculation. We set the z limit from 0 to 4 minus y, the y limits from x squared to 4, and the constant x limits from negative 2 to 2. Once the setup is complete, we perform the actual triple integration step by step using in function. We started by calculating the innermost integer with respect to z. We then take that result and integrated it with respect to y, and finally we take that result and compute the outermost integer for x. To wrap it up, we use the fprintf command to print our final answer to the command window. As you can see, the software outputs the exact value of the solid, which perfectly